This is one based on my master thesis at Bologna, and let's say based on some upcoming work which with Michele Cicoli, Fernando Quevedo, Gonzalo, and three. If time permits, I'll mention a word or two about another work I'm doing with Rakin Mohanto and okay. I'll try to list out some references as well to if someone wants to pursue or read some more. So I'll start with part 0, the type of the motivations. First off, I'll try to give a definition of what is actually string or what I try to do. It's basically pursuit of low energy quantum gravity that we try to produce particle physics plus cosmology. So starting with this, we need to have some basic facts. Some of this we'll try to address in this talk, and some of this we won't, or make at least some comment about it. So what are some basic facts about the universe we know? Let's say the universe we live in is 3 + 1 dimensional, and it's non-SUSY, or at least let's say SUSY is broken at a scale that we haven't observed. Second, it's, let's say, quite large, flat, and we are living in an era of dark energy, which translates to, let's say, which is saying basically the cosmological constant is greater than 0. And includes a sector of standard model, each group with chiral fermions. And lastly, this is the star, because emerged from a period of inflation. Okay, so in this work with these guys, we mainly try to address this part, which is basically saying that we are in an era of cosmology where our universe is expanding, and we have a positive cosmological constant. That is, we live in a de Sitter space. And then we also try to address this inflation. But we also made some comments regarding, let's say, this part, where we start from superstring theory, which is a theory of quantum gravity in 10 dimensions, and has SUSY. So the model we tried to build, or model that we worked on, has SUSY, and it's broken at a scale where we haven't observed yet. Of course, it should, these things put a bound on the theories that you're trying to build. And let's see, this is the assumption that we put while compactifying superstring theory. I'll mention this a bit more. And we also do make a comment about this, like how you can realize standard model like theories in this setup. Okay. So one of the first question is, if we want to do string phenomenology, why do we start with, let's say, I should have given the numbers. Why do we start with number 3? That is, okay, why do we start with the cosmological part? Let's say, why do we start with building a model based on cosmology first, then going to particle physics? Because the bounds on cosmology are a bit stronger than the bounds from particle physics. So, so there are some things. Okay, so we get bounds from cosmology, which translates to something, a bound or bounds on something called moduli. I'll define them in a bit, but first the bounds coming from cosmology or cosmology experiments, they put bounds on something called a moduli. You will define that soon.
So what do you mean by bounds from cosmology?
Okay, it can come from, let's say, the space telescopes or okay, one of the bounds, interesting bounds is the fixed force bounds or equivalence principle. So we don't really observe deviations of the equivalence principle. So what do? This puts a bound on masses of these moduli. I'll define them in a bit, or moduli fields. So these are some bounds from cosmology. So these bounds from cosmology or the experimental bounds are much stronger than the particle physics bounds. So we try to do cosmology first, then we try to build particle physics. So what is the starting point? The starting point is superstring theory is a theory of dense space-time dimensions. We try to decompose times some 6 compact manifold. This could be Minkowski PS, which is or AS. That is, we are looking at maximally symmetric spaces. And this is some compact manifold. Compact. So if you write the metric, you can decompose them as this, where my indices mu and nu run from 0 to 3, and m and n are internal indices or indices of this compact manifold, which run from the 4 to 9. So what we try to do is look for vacuum solutions. That is, solutions where if you use this part of that compact manifold, we try to look at solutions which are Ricci flat. So this gives constraint on the manifold that we're looking at. So if this gives a constraint and this is a 6-dimensional manifold, so what are the things that we want? One, on X6, things that we want about X6, one, Ricci flat. Two, we want to preserve some SUSY because supersymmetry makes things easier to work with. So preserve some SUSY. And we have a manifold which has all these features, which we call Calabi-Yau threefold, which is a complex manifold which has these features: Ricci flatness, and has some SUSY preserved. Of course, you can go into the mathematics where you can define Calabi-Yaos more properly, but that is what we need for now. So basically, when we're looking at the superstrings, you have these fields. Let's say if you have the metric, you have something called the B field. We haven't really coupled the matter here. So these are the fields that you get when you there's a sector which we call the NS sector. So that is the fields you get, basically.
But here you don't consider the B field and the.
But B field also, I think B field also respects the Ricci flatness as far as I know. Does it? Anyone?
Well, the equation is different. That's like so I think H squared in the.
You can do this, right? When we're looking at the module space, the way I go, you look at the deformations of the metric, and then you get the moduli fields like these scalar fields. That is, you can get there are two kinds of moduli fields you get from this that preserve the Ricci flatness: the scalar modulus and the complex structure modulus. I'm not sure if the B field.
I mean, you get Calabi-Yau if you set the H to 0, right? The field strength at B. Otherwise, you get some generalized Calabi-Yaus. Something more complicated.
Yes. Okay, yeah.
Calabi-Yau is
It's
a simple case you can consider.
Yes.
Yeah, actually, if you turn on B, then you have a separation of the Calabi-Yau cone or deformations.
Yeah. So if you turn on B field or the fluxes, you move away from the Calabi-Yau, you get this different torsion classes, and you have different kinds of. You can have a conformal Calabi. If you turn on the fluxes, we'll deal with a scenario where you have a conformal Calabi-Yau or a warped Calabi-Yau or different kinds. Yeah. If you turn on this, you'll move away from the Calabi-Yau. So, okay. So the problem is, we were at the stage where we have this Ricci flat metric, manifold, which gives Ricci flatness and preserves some SUSY. This gives something called a Moduli space of solutions. Again, I'm using the word, then I'll now define it. So as I was saying, we want to preserve the Ricci flatness, and we want to look at the parameter space where, or the range of metrics for which we have Ricci flat manifold. So this gives rise to a space of solutions, or let's say, which comes from deforming the metric by some factor, and it's still a Ricci flat metric. So these things gives rise to some moduli. Okay, now what is this moduli? I define it from 2 points of view. Okay, from a cosmologist's point of view, these are spin zero scalar fields with vanishing potential, or I could just say massless. You take two derivatives of the potential, you recover the mass. So from a cosmologist point of view, these are spin zero scalar field, which are massless. From a more rigorous point of view, you get this from, so in terms of Calabi-Yau, as I was saying, you deform the metric, you look at the space of solutions. This gives rise to some fields, which we call the Moduli fields. Okay. So we have actually a bit more, but okay. So we have two kinds of Moduli fields which arise from this deformation. That is, you want to deform the metric, you want to preserve the Ricci flatness, you get this Moduli fields, which are spin zero scalar fields. From that deformation, we get two kinds of Moduli, which is the scalar. We have H11 of them, and H11 is actually for those who know, it's the Hodge number, which is the dimension of the double cohomology group, and for others, it's just the number. So we have H11 of them. And there's another kind of moduli which we call the complex structure. We have H21 of them. Okay. So a side comment, those of us who were in Ricard's lecture on Sunday, he was talking about this Calabi-Yau manifold. Sorry, he was talking about the scalar manifold, which has this natural two form. That is, if you want, so a scalar manifold is a manifold which has a vanishing scalar form. So Calabi-Yau is a special kind of scalar manifold where you have Ricci flatness on top of that. So we get two kinds of moduli here, but this is not it. We have other moduli fields which arise from Kaluza-Klein reduction. So they can also be assigned some geometric ideas. P-forms or P-forms. So when we try to do a Kaluza-Klein reduction, there is we try to compactify on some manifold of some P-form fields or H fields, whatever. You get a bunch of scalar fields, which are these Moduli fields. Okay. So having this Moduli field aside, so this Moduli field has some uses. First, I can, in a scenario where I have just one scalar modulus or scalar modulus, I can write the volume of the internal space as something like this, where tau, I'm denoting the scalar modulus, which controls the volume of the Calabi-Yau, and the complex structure, which basically controls the shape of the internal manifold. And so we have denote the complex structure by U, and the dilaton by big S or sometimes small s, depending on mu. Okay. So yeah. So moral of the story, we have a bunch of scalar fields that we get from superstring theory in 10 dimensions. There are different kinds of them, and they are massless. What is the problem if we have massless scalar fields in the theory? The problem is that they would mediate long-range forces that we have not observed. as I was talking about the modifications of gravity, let's say equivalence principle, and all of those things which we do not observe at the energy scales now. So if they're massless, they would produce this fifth force, which we hadn't seen yet. So for all the modulus in the theory, we need to have masses or potential source. So this is the problem, or this is the field which we call Moduli stabilization. That is, we try to see if there are masses of this Moduli fields. And also aside from this Moduli fields, if you're trying to build a standard model, like model these Moduli fields, so string theory has no free parameters, basically. The only parameter is alpha prime, that is the string length. So when these Moduli fields give basically the coupling of the fields of the standard model. So when you try to build standard model, you cover interactions, the expectation value of these Moduli fields are basically couplings in the standard model like theory that you're trying to build. So if they're massless, that's issues because we have constraints, because we know how the parameters in the standard model are. Like we know how coupling works or these things. So or the masses of the particles in the standard model. So if these are massless, they will create issues for building particle physics models. So okay. So this is the end of part one. I will part zero. I go to part one where I review some things from literature. Okay, so this is based on this paper by Kuchlu, Kalosh, Inde, Trivedi, and plus LMT, where this is mechanism and Malasena on top of them. And then two.
So before you go to part one, what was problematic with the massless field?
So if you have massless fields, this would mediate long range forces that we don't observe. Right. And on top of that, in string theory, the expectation values or the couplings that you get if you're building string theory models, these are expectation value of Moduli fields. So that is problematic. For example, I don't exactly remember the form, but so if you have two fields that have some interaction between them, let's say some interactions, the Kähler modulus enters the coupling.
So, and also another question, you said that string theory have no free parameters,
Yeah.
and then you said except alpha prime
The string
or
length.
alpha prime.
The string length. So one parameter is the string length.
So it has
One string.
Yeah.
One parameter.
Wow, I wouldn't call it a parameter, it's dimensionful, so it's dimensionful, so
Yeah.
it just says the unit of dimension, so it's not really a free parameter. I mean, if you want to
It's-
talk about a
it's
free
a
parameter,
dimensionless.
it's a
Yeah,
dimensional free
dimensionless.
parameter.
So there's no.
There's,
okay,
I would say there's no free
dimensional.
parameter.
There's no free parameter.
The three dimensionless.
Yeah.
Yeah.
Okay. Okay, so I'll finish the so another part is Brane-Antibrane inflation by Brane-Antibrane in an inflationary universe by Fernando Mujumdar, Rajesh Kumar, and Okay, number 3. LBS. And Joe Oliver, I think 200. Okay. So, what do we know? For late times, we need a de Sitter vacuum. That is, if you're constructing a potential should be greater than 0 because we live in a world where the cosmological constant is positive. Okay, let's use minimum. Okay, so if we're looking at scalar fields,
So you're saying that some scalar field is set down the minimum of the
Yes.
potential so that they can be treated as the cosmological constant. So actually it's kind of a time varying cosmological constant.
yes. But
Yeah, just an observation.
yeah, I mean, de Sitter vacua, if you construct them, they are really metastable. Right? Like they're not really stable in quantum reality.
Well, it's not even clear that you can construct them, right?
Exactly. And then on top of that, there are some conjectures which constrain them, a bunch of no-go theorems. So I'm not sure. The constructions there are heavy criticisms of that constructions. Like the KKLT is a construction is a de Sitter construction. LVS is a de Sitter construction which has heavy criticisms, and it's a topic of it's a really hot topic even 20 years after this paper came out. Okay, so since we live in a 4-dimensional world, we are using superstring theory going down to 4 dimensions. So our theory will be described by 4-dimensional supergravity. So we have 2 functions which does the job for us, which is the scalar potential given by K and
So what was LES again?
large volumes.
And the BA?
I did the preparation last minute, so I should have put the archive number, but I didn't. So if you just put large volume scenario,
Yeah, and BA?
Brane-Antibrane inflation, Brane-Antibrane in an inflationary universe. That's the name of the paper. Okay. So scalar potential, superpotential. If you write this, if you write the scalar potential, it takes this form. Where the sum runs over all the moduli or all the scalar fields in my setup, and Kij is the inverse scalar metric. The W is the superpotential, and K is the scalar potential, and D is the scalar covariant derivative, which goes as and so since we can write the so this metric can be written in terms of a single function since we are looking at scalar manifolds. So it can be written in terms of a single function, which we call K. And yeah, this is the supergravity potential. A few comments. And I and J run over all the moduli fields or all the scalar fields in my system. And W is the superpotential. And I will now state a few things. The superpotential, it's called the book of Buckle superpotential, it depends on U. We have U.
Yeah,
U, which is the complex structure module, then S, the electron. So if you're trying to construct the F-term scalar potential, so you have the sum running over U, alpha, S, and T. If you look at it, you look at the potential for V, it vanishes at tree level. So if it vanishes at tree level, so it's still massless and we have problems. So using tree level results, when we try to construct the F-term scalar potential, we don't have a potential for tau, the Kähler modulus. So way out,
You're still in the situation where you only have one Keller model, so. This is more.
I think for all of them vanishes because the Google buffer window super potential is just on this, and you're trying to construct a supersymmetric minimum. Removing a lot of details, but since you're trying to construct a supersymmetric minima, you enforce those conditions. You look for the minimum of the Kähler modulus. All of them are unfixed. So way out. So until now we have been dealing with tree-level results only. That is the Kähler potential, the super potential. These are all tree-level ones. So the way out is to use quantum predictions. So the way out is quantum corrections. What can we do? We can use, so the Kähler potential, so a lesson from supersymmetry that we have, the Kähler potential receives both perturbative and non-perturbative corrections, but the super potential only receives non-perturbative corrections. You can do a perturbative, you can have a perturbative correction for the super potential. So way out, I just use quantum corrections. Let's see. So what KKLT had in mind? So KKLT in words, what they had in mind is, in addition to the, okay, I'm using another band notation. So small tau and big tau t are the same for now, but of course they're actually not. It's a multiplet, but it's fine for now. Let's say tau, small tau and or tau and t, big T are the same. So what KKLT had in mind is use a non-perturbative correction to the superpotential. So this can arise from instant-on effects, Higino condensation, and these things. But let's say you have a one non-perturbative correction to the superpotential. You look at the scalar potential. What you get is an ADS minima with some looks like this, but we don't want that. We don't like that. We don't live in that. So we need de-Sitter. What they did, what KKLT had in mind, what the guys had in mind was, so we call this uplifting, where we move from an anti-de-Sitter vacuum to a de-Sitter vacuum. So I'll try to draw a cartoon diagram that I will be using from myself as well. So they used something called an anti-D3 brane. So branes are these extended objects that we have in string theory, and so an anti-brane is something which is oppositely charged, RR charged compared to branes. So they use that, and the minimum they obtain is this error. Of course, there are some criticisms. Is one of the ones that I know is this might not be a stable setup. Let's use non-stable. And second, as it looks, they're using the tuning the superpotential, the tree-level result to be small so that it runs against the non-perturbative ones, or that competes against the non-perturbative correction. So W0, that is one of the criticisms. Okay, in this setup, I'll keep this diagram. In this setup, you can, this is a cartoon diagram for conformal Calabi-Yau, and this is some throat it has. So I'm not explaining it in detail, but so the antibrane sits at the tip of the throat, which provides a positive contribution and uplifts the vacua. And you can have standard model constructions on like D7 branes. This is a type 2D setup. You can have standard model on stacks of D7 branes. You can construct standard model here, and so on. Okay. So then so these are the two well-known decider constructions. What large volume scenario did was instead of one Taylor one, they considered two. So they call this Calabi-Yau of something called a Swiss cheese structure. It looks like a Swiss cheese. And one thing they did is consider two Taylor modules. And in string theory, there are two kinds of perturbative corrections. Superstring theory, there are two kinds of perturbative corrections that you can have, the alpha prime and G string. They use the leading alpha prime correction in type 2B, which occurs at alpha prime Q, and this is coming from the R4 term. So they use that, so they compactified on a Calabi-Yau. What this does, leading correction, is you can write the Taylor potential as something like this. So if you consider the leading correction, the volume is a bit modified, which gets to again where S is the string coupler. I should have drawn the diagram. So initially, KKLT gets this kind of vacuum, which is AES. If you're looking at the minima, it's negative. Using the uplifting, they obtain some decider solution. And so they also use some, in addition to this, they also use some non-perturbative correction. And again, the minimum they obtain is anti-decider. How do you get to decider? You again consider this anti-brane, anti-D3 brane, or there are other D-term contributions that you can include, and you can uplift decider. This is the main post or let's use the word post-inflationary construction. That is, we are looking at a construction of the current state of the universe where we have a dark energy dominated area. And this is two of the pretty well known constructions. I can do some honorable mention. Which seems better, but it hasn't been studied properly as of yet. It's called RG-induced so it came out 2 years ago, and this is by Fernando Quevedo and Kirchhoff. Okay. So in this way, we can construct post-inflationary or current state of the universe. So now, okay, I started 10 minutes late. Is it okay if I go 10 minutes over?
Yeah.
Okay, so I'll quickly talk about inflation. Should I take the assumption that you know what inflation is?
Can you roll out the other black box so you can see it?
So inflation. Okay. So I'll briefly say what it is. So it's a rapid era of it's a rapid era of expansion of the early universe. So if we have the standard Big Bang, that doesn't really solve the problems. So inflation that creates some problems. So inflation is an expansion where we have an exponential expansion of the early universe. So you guys have seen this advertisement by L'Oreal Paris. It says 5 problems, 1 solution. So inflation is 5 problems, it's all around 5 problems in standard Big Bang. I wanted to say a bit, but let's get away with that. So, as I was saying, it's an expansion. So, homogeneity and isotropy, if you ask the universe as we see that to be homogeneous and isotropic, everything boils down to something called scale. So, during inflation, one of the ways to define inflation is to have okay. So the lesson we had from inflation is that the requirements that we put on inflation is that the universe should have expanded by 16 equals or 16 exponentially 60 times. So in the early universe, to avoid problems that of standard Big Bang cosmology, we need an expansion by 60 e-folds. So we need, in the early universe, we need inflation to happen and persist long enough. So these are guaranteed by two quantities, which we call epsilon and eta parameter. Oh, I should have mentioned something. I should have mentioned how we describe inflation. So the reflective theories of inflation can be described by a scalar field with the requirement that its kinetic energy is much less than potential energy. So we have something called slow roll. So we need a slowly rolling field to have inflation. And we need these parameters to be much less than 1. Because we want an accelerated expansion of the early universe, and we want one to have expansion or acceleration to have existed for a sufficiently long time. So these two parameters, being less than 1, guarantees that. For this is actually the kind of version. Can you find them? This one in from factors. So these two quantities guarantee that inflation happens and persisted long. So inflation is quite nice because a lot of potentials satisfy this criteria. For example, we can write potential as simple as this, and you can get away with slow inflation. Or you might be very creative. Let's say you write potential this some factor, non-negative. I think it's p factor. Yeah. So you can get away with inflation with even this kind of easy potentials. So this is a brief one on inflation. So for the requirement we get is for inflation, we need an accelerated expansion, and it can be described by a scalar field satisfying the criteria that its kinetic energy is much less than its potential energy. And of course, it has some parameters to satisfy epsilon and eta. So this is the lessons that we learned from inflation. Yeah, given the references before? Yeah. Okay. So the idea is quite simple. Let's start with the brane. For example, but usually it would work for any DP things. So you start with D3 and D3 bar, Brane-Antibrane. The idea is quite simple. Their separation gives you let's call it Y, the inflaton. Or the inflaton is the field that we're scalar field which causes inflation. Okay. And then we can write the potential for it. So this B and omega are some numbers which, if I say it doesn't matter, it's wrong. It does matter. It depends on the warping. If you're in this scenario, it depends on warping, how warped your manifold is, Calabi-Yau is, and it depends. It also has factors of G string and so these things, because if I'm thinking about it, these are Brane-Antibrane. They'll have some tension, they'll have these things. So, but I'm not writing those out. Let's say we have a simple potential. This can cause inflation. So these guys checked it, they studied this analysis, but the early paper by these guys, they had problems because they were not getting inflation in a controlled setup. So what, because one thing, two of the criticisms were, one, they didn't address moduli stabilization. What I mean by control setup was it was not that easy to get those parameters to be less than one or for inflation to happen. And one side remark, I think this paper, I think came out in 2001 or two, I don't remember exactly. It is the first string derived inflationary model, where, for example, when we try to do inflation, we say that there is a scalar field. We don't know where the scalar field came from. We don't know what that scalar field is. We just consider that scalar field and let's say study its dynamics. But what these guys did was one of the, I think it was the first idea where the inflaton has a natural origin.
This is, I believe it's, weak field case. I mean, this goes from unstable maximum to a minimum, right? This potential.
Yes.
I mean, it's not chaotic, for example.
It's actually, now that you mention, it's I'm skimming over details as much as possible. So it's actually a hybrid inflation. So you have a Brane-Antibrane, they come close together, they go to substringy distances, it becomes tachyonic, it means you're expanding around a maximum, as you said, and then the branes could annihilate, could form a bound state, we don't know. But according to, I think, Ashok had a paper in the late 90s where he was talking about this annihilation, and he wrote down a potential using string field theory where you have this Brane and an anti-Brane coming together, annihilating, and those scenarios. But best of my knowledge, no one has really seen in this inflationary mechanism if they actually annihilate or, I don't know, maybe form a bound state. Because why is this important? Because if they annihilate, they will have some energy release, or so these things. And this will affect the reheating error. So I am not sure if someone has computed them properly, but again, in this work, we are trying to see that as well. So if they annihilate, but I don't really understand the setup.
Doesn't potential come from some, reason, for example, supersymmetry?
These are really, here I'm just writing out things. these have proper origins. For example, they compute, there's something called an open string moduli, they computed the amplitude, they looked at everything properly and found out this potential. So, yeah. Okay. These guys then addressed it, looked at this setup where you can have this D3 grain, which is free to move around, causes inflation, and you have a good scenario. But the problem later found out was whenever you try to do this stabilization or moduli stabilization scenario where you try to stabilize the moduli using non-perturbative corrections, you have something called an eta problem, which says that you generate corrections to eta, and these are order 1. So it causes problem because if its eta is order 1, then inflation will happen for long enough time. So way out is again perturbative stabilization, which is basically this. What we try to do. Let's use PS, perturbative stabilization, or, okay, what is perturbative stabilization? So there are two corrections that you can get in string theory, the alpha prime and loop corrections. You use those alpha prime and loop corrections to generate a potential. This is perturbative stabilization. So previously what LBS and KKLT did, so what LBS and KKLT did was use non-perturbative corrections. So we were trying to study initially, firstly in the master thesis, if we can see, if we can use this alpha prime and loop corrections to see if we have a de Sitter vacua or during inflation, if we can stabilize all the movement. So perturbative stabilization is a bit better because usually we know that perturbative corrections are more important than, let's say, very bad wording, but non-perturbative corrections are usually smaller, unless you're, of course, QCD, you can talk about QCD, but non-perturbative corrections are usually smaller. The second, as I mentioned, the 3 levels for potential needs tuning in KKLT or these kind of scenarios. So this doesn't need tuning. Tuning in the sense that W0 should be much less than 1. One thing that I should mention, but recently the Cornell group has been studying these cases or those Calabial where you can have actually realized KKLT, and they found a whole bunch of it. So this might actually not be very unnatural, that W0 is much less than 1, but okay, but it's still a tuning. And third, no eta. That is, you don't, okay, I erase this, you don't generate corrections to the eta parameter and it doesn't become order 1. Okay, so what ingredients we use. So we started with the known alpha prime and loop corrections. First, something called the BHL piece, named after the authors. They looked at, I think they tried to see what corrections we get for when they compactified on the Calabi-Yau. And it's the leading alpha prime correction. It's an alpha prime cubed. So that's the leading correction you get is superstring theories. And it's coming from the R to the fourth term. So you have these higher derivative corrections, which are alpha prime corrections in string theory. This correction comes from the R to the fourth term. And of course, it modifies the volume by some zeta over S is 1 over GS, and zeta depends on the Calabi-Yau, sorry, the oil character of the Calabi-Yau, some numbers. Then there was this correction, this logarithmic corrections at alpha prime cube and one loop, G string, which logarithmic means it's direct scalar potential. This is some coefficient of the logarithmic piece, and this is the logarithmic correction. Then you can have some Moduli redefinition. There's a freedom to do some Moduli redefinition. And that too depends on the logarithm of the volume. And you have some loop corrections. So we were kind of conservative with our approach, where we only looked at known corrections. And I will mention one criticism at the end of it. So there were two of them, which called the KK loops. These have specific ways they have been computed. They looked at these 7 branes and the KK mode exchange between them. So this is at the level of the Taylor potential. This is known as S over tau. S A is a function, some function of mu alpha the dilaton. Some winding loops, which again comes from the exchange of winding modes between stacks of intersecting branes, and some order of correlation, which doesn't really become helpful, but it's not setting. Okay, I'll quickly sketch what we did. So we considered this corrections to the Taylor potential. We then did a Moduli definition, looked at the from scalar potential. We get a term like this. The leading 3 terms. where A is equal plus B is or something is so if we want to have a minima, we need these terms to compete. And we looked at the parameter space where they compete and tried to see what happens. We found a DS vacuum with no uplifting required, of course. And what we found is no uplifting required just from perturbative conventions. We got this. Two, no W0 Q. Three, gravitational mass, or let's say SUSY, constraints to be broken, plus there are some phenomenological constraints satisfied, and tau at the minimum is exponential s over time squared, roughly. So it's quite large, and you have a very large value of tau. So this is important because there are some constraints coming from experiments. So this is good because a bit better than before because we had no uplifting required, no extra ingredients, just using perturbative corrections, we find a minimum. This is for the post-inflation part. For the inflation part, I will quickly mention what happened. For the inflation part, same exercise, because we need to stabilize the moduli. Otherwise, again, this is problematic. Did the stabilization during inflation, looked at the parameter space for all of these coefficients and see if they're satisfied. Looks until now looks good. So a few comments that about number three. Number three, what we are trying to do with Rakin is this is for just one model. We'll try to, a natural question to ask is if we can do this same exercise for all of the moduli, or I don't know, 5, 10, just increase the number of moduli because it would be nice to see if we can do the stabilization exercise with these moduli. Some possible criticisms I will just quickly mention. So this correction were computed in toroidal cases and conjectured for Calabians. So if you look at the loop corrections, they were computed for toroidal cases, not Calabians, but they were conjectured to have this form for Calabians. Same for number 2, I guess. Not sure. And this is a possible criticism. And second, if you notice, we did not at all talk about the complex structure moduli and S. It's my personal complaint or criticism is that if we're stabilizing it, we're changing the values of S and U, but we are not really, we are under the assumption that U alpha and S has been stabilized and has a specific value. And number 3, these coefficients that we have been using for the stabilization, this, does it affect this plus because what we have done is just looked at the cosmology, not particle physics. Yeah, this is it. Thanks.
Okay, do we have any question?
So are the perturbative corrections under control here in the sense that higher corrections will
Yeah,
give a smaller contribution?
Yeah, it should. Otherwise, it's a breakdown of the perturbation theory.
Exactly. So what's the value of the string coupling, for example, in your case? Can you
We get
make it small enough that?
we get really dangerous bounds on it. For example, it's less than, if we put on the experimental values, I was doing it yesterday, it should be less than 20. S should be less than 20, so S is 100 yes, less than 20. These are the bounds that we get from cosmology. So not too bad, I suppose, because it's, what is 1 over 20? It's 0.05. Yeah. But again, my personal doubt is that if you're doing these corrections, I don't know, I will talk with others about it, but we change S, right? And again, it would be nice to see if these things can be computed properly. And again, as with what you were doing, for toroidal cases, if we can have the full R4, this can be used better for understanding if, or if there are other moduli. We have just one. And these help in the stabilizing one modulus. If you have more of these, like computed, it will help better and it will give a better understanding of things for sure.
This is your previous work or current work?
This is all current. Previous has factors of G-string which are incorrect, factors of numbers which are incorrect, factors of matrices whose inverse is not correct.
But the results are fine.
The results are fine after some corrections. This correction, I mistook it, and for me, these guys struggle for 3 months. So up to some degree, factors.
Mentioned this thing with comparison with the sense model of the Brane-Antibrane.
Yeah.
I think in that case, what he was doing was considering the Brane-Antibrane, but the branes were unstable, I think. Your branes are stable. And it turns out that for a sense model, you have Brane-Antibrane, and then they decay, and they do not form a bond state, but that is like, it's like the way to model it like an instant one, in such a way that you go from one vacuum to the other. If that were the case in your model, then you will have some new values for the modular. I think that will be the only thing that might change as far as I know.
But that is, I mean, so this paper by Mabu, Fernando, and these guys, they had a scenario where, so this, okay, I was telling you this, there's this old paper by Brane-Antibrane and Mappa in the 80s. So they talk about how superstring theory is stable if we have 4 non-compact dimensions. So they give some thermodynamic out of it. I don't remember the paper, but it's Baffa and Brane-Antibrane in the late 80s or something. So these guys expanded it for the case of branes. So if you have branes, and these branes are decaying via this BV mechanism, the Brane-Antibrane Baffa mechanism, and in type 2b, they were saying that you are left with a system of D3 branes. But I think, I don't know, but some of the papers I've seen are these form bound states as well. But I don't understand this properly. I want to understand this properly, so I'm mentioning this to you, that we are trying to see what happens if they annihilate, for example, in their idea, in the paper in the inflationary paper, Brane-Antibrane inflationary paper, they started with D9 or D7 branes, it started decaying, and they had a system of D3 branes. So this D3 and D3 caused inflation, and if you have a system of D3 branes, you can construct, you can have a stack of them, produce the standard model, and do particle physics with them. But the question is that I have is if these are really stable, or I don't know if this from some bound state.
And about the thing that Giacomo asked, to add matter to the models. Whenever you have brains, there is a well-known way to add matter to this thing, right? Do you do it in the same way, or which kind of matter are you?
So I was saying you did cosmology first, then particle physics. So if you try to add matter, you can do that, right? You can have D branes.
You're working still with just 1D3 and 10 and GD3.
Yeah.
Then you are talking like put a stack and do this.
Standard model. We are talking, we are not doing.
But I mean, aside from that, you have these models, then you can put extra, say,
Yeah.
flavor brains.
Yeah.
But then they will break supersymmetry in a non-trivial way, right? Or I do not know in which way you are breaking here supersymmetry. I think it should be like very.
I have mentioned that we are using. I mentioned that to you. We're using this nilpotent superfield, like the Ghostino, that gives the Ghostino. We have a nilpotent superfield that breaks the SUSY. So the nilpotent superfield is on the anti-brane. It breaks the SUSY. So that is what we were doing.
Okay, but in case you add more matter in terms of, I mean, as brains, then I think for sure likely you will be breaking SUSY before that mechanism happens, I think. I mean, otherwise you have to be very careful in which brains you are allowed to add and which matter you have to add, etc. etc. Are there more?
There are models. So okay, yeah. At the top of my head, the ones I remember is, of course, this paper by Michele and Francesco Mia. You can look at how they did it. They considered this correction, and I don't remember because I looked at it quite. It's a very old paper. It's 2015. It's okay, not very old. Yeah, 2015. So they tried to do it with yeah, they try to build standard model with like this, but I don't know if someone has properly done it with all of this setup. I don't think so. Because once these are fixed, these will affect your standard model gauge couplings. This will affect how like even hierarchy of scales. So I don't think so. First step is doing the cosmology first, because the bounds are stronger from that. So next step is particle physics. Thanks.
Also, that after reheating, actually you have to interaction with matter.
Yes, but the idea is, as far as I understand the reheating part, I'm not much strong on that setting, but so the inflaton basically decays into the standard model part. So if you have the inflaton decaying, but in this case, I'm not sure how this would work. But of course, you can build, as he was saying, as Salman was saying, you can build standard model with stacks of D7 brains and these things. So you have standard model like model, you can play around. Of course, you will have, but if you do the Moduli stabilization first, all these things first, you'll have strong bounds on how you can affect. But these are fixed, like if the couplings would be fixed, everything would be fixed from these calculations.
So this is basically a cheating mixture of top-down and bottom-up approach.
More questions?
That's it, speaking, yeah.
I like your t-shirt.
In the email you wrote down that you are bringing